In the vacuum of outer space, two pieces of bare, highly polished metal do not merely touch, they instantly fuse into a single solid object. Without air or surface contaminants between them, individual metallic atoms cannot distinguish one piece from another. This natural phenomenon is formally known as cold welding, or solid-state adhesion. On Earth, manufacturing requires extreme heat, pressure, or electric arcs to melt metallic joints together. In space, direct atomic contact alone triggers the exact same permanent metallic bond. If two clean copper bars are pressed together inside an ultra-high vacuum chamber, the boundary line between them vanishes. Electrons begin flowing freely across the interface, creating a continuous crystalline lattice with up to 90% of original structural strength. Such a remarkable process occurs without any melting, heating, or visible sparking on screen. To a human observer, the separate metals simply stick together instantly, as if joined by an invisible, unbreakable adhesive that transforms two components into one monolithic block. Early space pioneers in the 1950s were largely unaware of this atomic hazard. They assumed mechanical hardware would behave in orbital flight exactly as it did on laboratory test benches, operating with predictable sliding and rotational friction over long missions. That oversight cost millions of dollars and severely damaged real space missions. Antennas failed to unfold, mechanical switches seized in position, and moving joints locked up permanently, leaving ground engineers utterly helpless to repair them from millions of miles away. Yet cold welding is not a bizarre or artificial force. It is actually the fundamental, default state of bare metal when stripped of the protective atmospheric envelope that constantly shields our planet and alters every metallic object we handle every day. On Earth, every metallic object is wrapped in an invisible, microscopic shield. The oxygen present in our atmosphere reacts with raw metal surfaces almost instantaneously, forming a dense oxide film just a few nanometers thick across every exposed square millimeter. This delicate oxide coating, combined with absorbed moisture and atmospheric hydrocarbons, prevents metal atoms from touching directly. Even when pressing two steel spoons firmly together, their underlying atomic structures never actually make true physical contact across the boundary layer. In 1965, researchers at NASA Lewis Research Center began studying mechanical contact inside simulated space vacuums. Donald Buckley and Robert Johnson discovered that scrubbing away this oxide film caused instant, catastrophic surface seizing on rotating mechanical components. Inside custom vacuum chambers pumped down to 10 to the -9 torr, metal pins sliding against rotating alloy discs welded solid within seconds. Mechanical friction rapidly wiped away the protective oxide film, exposing raw, unpassivated metal underneath. Once that protective oxide film was destroyed, exposed surface atoms instantly reconstructed their shared metallic matrix. Buckley and Johnson measured friction coefficients jumping from 0.2 to well over 10, effectively locking moving assemblies into a single solid block. Their groundbreaking research proved that atmospheric corrosion is the primary reason terrestrial machinery functions without seizing. Without oxygen continually repairing microscopic surface scratches, everyday items like door hinges and automobile pistons would cold weld during normal daily operation on Earth. Scientists quickly realized that launching unshielded metal hardware into space meant placing it inside an environment that gradually strips away protective oxides over time, converting routine mechanical hinges and sliding joints into permanent, unintended structural welds. Popular space legends often claim that spacecraft will instantly freeze into a solid, useless ball of metal upon entering orbit. That is a persistent myth, because equipment manufactured on Earth carries its native oxide layer directly into the space environment completely intact. Cold welding actually requires two strict conditions: bare, unoxidized metal surfaces and direct physical contact. In orbit, mechanical parts only fuse when sliding friction or extended vacuum exposure wears away that initial protective oxide film, exposing pristine atomic layers directly underneath. In April 1991, NASA encountered a critical operational failure on the Galileo spacecraft en route to planet Jupiter. Its primary high-gain antenna, designed to unfurl like a giant umbrella, failed to open properly, threatening the entire scientific mission. Engineers discovered that 4 of 18 titanium ribs were jammed tightly in their sockets. During ground transportation by truck across the United States, subtle road vibrations had rubbed the protective dry lubricant off the locating pins, exposing bare titanium underneath. Exposed to space vacuum during flight, those unlubricated titanium pins fretted against their sockets during deployment maneuvers. The surface oxide coating scrubbed away completely, causing the bare metal to cold weld into place and locking the primary high-gain antenna shut. Ground controllers spent months repeatedly pulsing onboard thermal heaters and hammering the drive mechanism to break the cold welds, but the titanium held firm. NASA was forced to rely on the low-gain antenna, drastically reducing overall data transmission rates. The Galileo mission proved that cold welding does not happen by magic or instant contact upon reaching orbit. It is a subtle mechanical failure triggered by microvibrations, vacuum degassing, and unshielded friction scrubbing away protective surface oxide films over time. To understand why cold metal welds without heat, consider how metallic bonds function at fundamental levels. Unlike covalent or ionic bonds, metal atoms float inside a shared sea of delocalized electrons that flow freely between positively charged nuclei. When two oxidized metal surfaces meet, this shared electron cloud is blocked by non-conductive oxygen atoms. But when two clean metal surfaces touch, those electron clouds merge seamlessly, creating a single, continuous electronic structure across the entire boundary line. At the microscopic scale, the atoms on the outer surface of one bar cannot tell that the adjacent atoms belong to a separate object. They simply fall into the lowest available energy state, which forms a single continuous crystal matrix. Surface roughness plays a critical role in this physical process. Real metal surfaces are never perfectly flat on atomic scales. They feature microscopic peaks called asperities. Initial contact between two objects occurs exclusively at these tiny, raised surface points. Under mechanical pressure, these microscopic asperities deform plastically, flattening out and breaking through any residual surface contaminants. The tiny real contact area experiences immense localized stress, triggering instant atomic adhesion across those specific, microscopic junction points. Similar metals, like copper on copper or aluminum on aluminum, weld together far more readily than dissimilar metals. Identical crystal structures allow surface atoms to interlock perfectly across the boundary without geometric distortion or atomic lattice strain across the interface. This atomic compatibility explains why satellite mechanisms made of uniform alloys are particularly vulnerable in orbit. Without specialized surface coatings or dissimilar material pairings, identical metal components in sliding contact will inevitably bond into a single solid piece over time. Modern aerospace engineering relies on strict design protocols to prevent unintended cold welding in space. Standard guidelines established by NASA and the European Space Agency strictly govern every moving mechanical assembly sent beyond Earth's protective atmosphere today. Engineers coat critical space mechanisms with specialized dry lubricants like molybdenum disulfide. Unlike liquid oils, which rapidly evaporate into the vacuum of space, these solid film coatings provide a durable physical barrier that prevents direct bare metal contact. Moving spacecraft parts are also engineered using dissimilar metals with mismatched crystal structures, or hard ceramic coatings like titanium nitride. These materials refuse to share electrons easily, preventing solid-state adhesion even under severe mechanical loads and high contact pressures. However, cold welding is not merely an orbital hazard, it is becoming an intentional manufacturing tool. On future lunar bases, vacuum conditions will allow astronauts to assemble structural beam segments without using high-heat welding torches or consumable filler metals. By cleaning metal joints with ion beams inside the lunar vacuum, construction crews could cold weld large satellite dishes and habitat frames instantly, producing structural joints as strong as forged metal with zero high-temperature energy input. Nanotechnology researchers are already using cold welding on Earth to build submicrometer electronic circuits. Single crystal gold nanowires touch and fuse in seconds, forming seamless, highly conductive electrical connections without causing heat damage to surrounding fragile microchips. The exact same atomic force that once crippled space probes now offers a key to off-world construction. In the clean void of space, metal reveals its true nature, ready to bond permanently whenever atmosphere gets out of the way.